Hello AP Stats. Here we're doing our final section in the book of notes on logarithmic transformations and power transformations. And so this is a little tough, so I really want you to pay attention and go through these. Hopefully you've printed out these notes. First of all, when you have a list of data, you should always start by plotting it and looking at it. Remember though that if it is not seen to be a linear relationship, if it looks somewhat like a parabola or has a curve to it, we might need to transform it and look to see if there's another kind of relationship. Remember that R and R squared, meaning the correlation coefficient and the coefficient of determination, are only for linear data, so it doesn't make sense to talk about it if we're not talking about a linear relationship. A residual plot, of course, tells us if a linear model is appropriate. So we'll always look at that first. Here is an example of the length of year for a planet based on its distance from the sun, as to how long it takes, what a full year would be because of its length, its distance from the sun. And here's the table. Distance in millions of miles and number of Earth years. And first of all, let's see that the data have a curved relationship, and so we put on the y-axis the distance, on the x-axis the length of what a year would be, and we see this definite curved relationship. Now if we put a line across there, the R would still be fairly strong linear relationship, but we can clearly see that there would be a better model. So we check the residual plot to really get a good view of it, and we can see that definite pattern here. So that's not good, so we should look for a different kind of model. So these are the different models that we would consider using. Know that the ones we're going to talk about in this class are a power model and an exponential model, but there's all kinds of different models that could be used. Exponential models, some possible example would be salaries, like Major League Baseball salaries seem to increase exponentially. Prices of things like drugs, meaning pharmaceutical drugs, the population of living things, human population, of course, increases exponentially. So a lot of times you know which models to use just based on what the data is you're given. A power model, things that are related with a power. If you think of things like geometric relationships, like the area of something circular, for instance, area is pi r squared of a circle. So that's a power model. You are squaring it. But any area, volume, these geometric relationships would be power. Weights and relationships between living things, sizes of living things, would often be power models. So sometimes you can just get a view of which one to use from the data. Here's some pictures that we should know: exponential growth and exponential decay, which we studied in pre-cal. And we should recognize this. This is, of course, x squared, x cubed. So these are power models. So an exponential model would be something 2 to the x, 10 to the x, e to the x, or 2 to the opposite x, if it's increasing or decreasing, where a power model will be x to a power, or a number times x to a power. This one might be 1 over x, which is the same thing as x to the negative 1. So that is also considered a power model. This could be the square root of x, which we could write as y equals x to the 1/2. So that would be thought of as a power model. So if we take these two relationships, let's look at one of them at a time. Exponential model, x will be the exponent. A and b here are not varying, they are constants. For a power model, x is to an exponent, and it is a constant exponent. So a and b here are again constants. So how could we transform them to make them look linear? On both of these, I'm going to look at one of them at a time. cover this side up. We'll first look at the log model, meaning the exponential model. If I take this exponential model and if I start out and take the log of both sides, so I'm taking this and taking the log of both sides. We know that if we are multiplying under one log, we would split it up to addition, so make sure you understand that. And here I've taken the exponent from b to the x and brought it to the front. And so now look, we have somewhat of a linear relationship. This is a constant, and when x is 0, this is going to be the constant. So this value, the log of a, is our y-intercept. This is our little a here. And the number that's multiplied by x, the log of b, is now our slope. So this is a new linear relationship. We just have a different y-intercept and slope, and these are constants, so we can just call them a or b or whatever we'd like. So here is our actual model. Log of y, because we still have the log of y on this side, equals a plus bx. And this is predicted y here. And so we're going to use that to graph our data, and it's going to look linear instead of curved like it did before. Now what if we wanted to predict? What if we wanted to plug in an x to get back a y? Well, we'd need to change this back into exponents so we could find that y hat. And we know 10 to this equals y hat using the definition of what a log is. So 10 to the a plus bx equals y hat. And so we can just use that and plug in whatever x is to find our predicted y. Or we can split it up into these models. See here, I'm adding these exponents, so I can split that up to 10 to the a times 10 to the bx is another way I could write it. Either one you can use. And remember, if you took the ln of both sides instead, which is sometimes easier because ln is sometimes easier to find on the calculator, it would be e to the a times e to the bx. We could use that also, or e to the a plus bx. Either one is fine. Just be careful if they use a natural log on their graph, you need to make sure you transform using e. So that's our transformation for exponential model. Let's look over here for a power model. So if we, starting right here, take the log of both sides, and I have log of y equals log of axb. Just taking the log, I could have taken the ln of both sides. I split that ax into multiplication and brought the b out in front. And so now, again, this is our y-intercept because that's a constant, but our slope is just the b. And our whole explanatory variable is becoming the log of x. So b is the slope, the y-intercept is log of a, which that'll all kind of wash out as we go. And so the difference here is before, on an exponential model, we would end up graphing x against the log of y because that's what we ended up in our least squared line. For a power model, we're going to have two logs, log of x, log of y. I always remind my classes if you need more power to carry more logs. So we have log of y hat equals a plus b log of x. And so if you need to predict, we'll put our hats here, 10 to all of this, well, that looks a bit of a mess, but you can definitely use that way to predict. But if we simplify that, we'll end up with 10 log x, which is just x, because we have 10 to the log base 10. So we could also predict this way: 10a x to the b. Plug in an x. We'll have a and b, and find out what y hat equals in that situation. Okay, so if we want to graph them to look at a linear relationship, as I said, for an exponential model, you're going to put x, which is generally list 1, here on your x-axis, and log y. So we put under list 2, we would put our y values, and so maybe list 3, we would put the log of the x values, and list 4, we'd put the log of the y values. So this would be list 1 against list 4, and this would be list 3 against list 4. Log x against log y. Here's our reminder: more power for more logs. Okay, so our least squared line, what we had before, is represented this way. So if we actually had to explain it, we'd say the log of GPA, for instance, equals, these will be actual numbers, 2 plus 0.01 times x would be a variable like the amount of sleep you get. And then here's the transformation equation, and there it's the least squared line for a power model. So here's kind of our steps as to what we will do as we go through this. First of all, go ahead and run XY's regression. Look for the curve in the scatter plot and a pattern and residual plot, so you know that you have to use a transformation. Number 2, in list 3 and 4, put the log of x and the log of y, and plot the new scatter plot, and run the new regression against x log of y and log of x log of y. So you can see which one seems to be better. Does it seem to be a power model, or does it seem to be an exponential model? To see which one's better, look at the plots, look at the type of data there is, look at r versus r squared, which one's better. Remember, this is explaining the linear relationship that you have just transformed. And sometimes these numbers are very close between the power and the exponential. And we'll talk more in class about looking at the ratios between the two. And then last one, interpret and predict using logs. So when you're doing a prediction or you're interpreting, you're going to use logs to do that. So it might help a little bit to read this second section of the chapter to get some actual data in here, but we will be working on that in class. So make sure you have all these notes filled in. Thanks.